In this video, we are going to graph polynomial functions from its factored form. Our first example asks us to graph the function y equals x times x minus 3 times x plus 2 times x plus 1. In order to graph this, we need to figure out a few different things. First, we need to figure out the degree of the polynomial, the sign of the leading coefficient, the x-intercepts or the roots or zeros of our equation, and our y-intercept. To figure out the degree and the sign of the leading coefficient from the equation, the degree is going to be equal to the number of roots or the number of zeros of our function. And we know that from our investigation that we did in the last section. The number of roots then for this function is 4, because if we set y equals 0, then 0 equals x times x minus 3 times x plus 2 times x plus 1. We would have 4 roots because we would solve for each of these components equal to 0. The degree then is going to be 4. The sign is going to be positive, because if we expanded out this polynomial, x times x times x times x, there's no negatives in front of our x values here. That means that our sign of our leading coefficient is going to be positive. Finding the x-intercepts then, setting each of these to 0, we would have 0 equals x. 0 is going to be one of our intercepts. We would have x minus 3 equals 0. X equals 3 is another one. We would have x plus 2 equals 0. Another one then would be negative 2, and our last one, x plus 1 equals 0. Negative 1 would be our last x-intercept. To find our y-intercept, we're going to set x equal to 0. Let's just do this down here. We would have y equals x, which is 0, times x minus 3, 0 minus 3, times 0 plus 2, times 0 plus 1. If we solve that, y equals 0. Our y-intercept then is equal to 0. Because we know the degree is 4, this is going to be an even degree function. The leading coefficient is positive. That means that our end behaviors, as x approaches positive infinity, y is going to approach positive infinity. And as x approaches negative infinity, y approaches positive infinity. So our function's going to end in those two quadrants. Let's label our axes x and y. Each of these squares is going to represent one number. Please get into the habit of labeling all of your axes. I'm not going to do it here because it's going to get pretty crowded if I do, but do so on your example. Let's put in our x-intercepts. X equals 0 goes right here. 3, we've got negative 2 and negative 1, and our y-intercept 0 is already graphed. We now need to connect these points. So basically what you want to do is make sure that your end behaviors match up. Each of these is going to pass through the point. It's going to come back and pass through this one, pass through that one, pass through the final x-intercept, and then go back up. Don't worry about the local maximum or minimum values. As long as you're graphing your x and your y-intercepts accurately and your end behaviors fit with the function you're graphing, then you would get this correct. The relationship then between the x-intercepts and the equation of the function, to find x-intercepts, we are going to set y equals to 0 and then solve for each of those factors. And then to find our y-intercept, we set x equals to 0 and solve for y. I'd like to show you 3 more examples then. Our first one, if we find first, let's find our x-intercepts. X-intercepts for this one is going to be negative 1. For this factor is going to be plus 2. For this factor is going to be negative 3. Finding our y-intercept, we're setting x equal to 0, so we would have y equals 1 times negative 2 times 3 gives us negative 6, which would happen right here. We have a degree of 3, which is odd, meaning that our end behaviors, as x approaches positive infinity, y approaches positive infinity, and as x approaches negative infinity, y approaches negative infinity. Joining our dots then, we're just going to curve it around, would look like this. Our next example, y equals x minus 2 squared times x plus 3. Let's do our roots first. For this first factor, that would be x equals 2. For the second one, it would be x equals negative 3. Finding our y-intercept, we're setting x equal to 0. We would have negative 2 squared times 3 gives us 4 times 3, which is 12. Let's just make each of these boxes 3, so 12 would put it here. Now our degree is odd. Our leading coefficient is positive, meaning that as x approaches positive infinity, y approaches positive infinity. As x approaches negative infinity, y approaches negative infinity. So we need to join these points now. And the only way to do so, we start here, we go through our y-intercept, and we would actually do this. So the reason we do this is because this factor here is a repeated root. So anytime you see a squared, what will happen with a function is it'll come down, it'll touch the x-axis, but it doesn't cross the x-axis. It actually goes right back up. Kind of like a quadratic, because we have a square here. If the factor is repeated an even number of times, it touches the x-axis but doesn't cross. Our last example, y equals x minus 2 all cubed. Finding our x-intercepts, x is going to be positive 2. Finding our y-intercept, we're setting x equal to 0, so that would be negative 2 all cubed, which gives us negative 8. Let's make each of these boxes 2. Our negative 8 would be here then. Degree of 3, odd degree function. Our leading coefficient would be positive. Similar behavior as the other ones. We're going to have, as x approaches positive infinity, y approaches positive infinity. And as x approaches negative infinity, y approaches negative infinity. When we have something that's an odd number of times, when a factor is repeated an odd number of times, you can think of the function y equals x cubed. Now, when that crosses the x-axis, it does so, but it kind of squiggles through. Anytime you have a factor that is repeated an odd number of times, it will cross the axis, but it's going to squiggle through. And that's for things like x cubed, x to the 5th, and so on. If you had just x, it would go straight through, because that is like our straight line.